Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let's see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 45 kN acting at 2 meter from the point A. In the span BC, we are having UDL 15 kN per meter acting for the full span. In the point A, we are having a fixed support. In the point B and the point C, we are having hinged supports. Span AB is 6 meter long and span BC is 4 meter long. The moment of inertia for the span AB is 1.5 I. For the span BC, the moment of inertia is 2I. In this beam, we have to find three moments. In the point A, we are having a fixed support. In the fixed support, there will be a moment, that is MAB. In the joints, there will be two moments. In this beam, we are having a joint, that is joint B. In the joint B, we are having two moments, MBA and MBC. In the point C, there will be no moment because it is a simply supported end. So MCB is equal to 0. So totally we have to find three moments, MAB, MBA and MBC. Also we have to find three reactions, RA, RB and RC. Now let's make the fixed end moments. First, let us make the fixed end moments in the span AB. For making the fixed end moments, we have to assume every span as a separate fixed beam. You can see that I have made the span AB as a separate fixed beam. Now let's see the formulas to find out the fixed end moments. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load. That point load is not acting on the center, so we have to select this condition. The formulas for the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. In the span BC, there is UDL acting for the full span, so we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let's apply the formula and find out the fixed end moments. In the span AB, the point load is not acting on the center. We already saw the formulas. Let's apply the values inside the formulas. W is 45, A is 2, B is 4 and L is 6. After calculation, we are getting M of AB is equal to minus 40 kN meter and M of BA is equal to 20 kN meter. Now let us make the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments. Let us apply the values inside the formula. W is 15 and L is 4. After calculations, we are getting M of BC is equal to minus 20 kN meter and M of CB is equal to 20 kN meter. In the moment distribution method, we have to calculate the distribution factor. We have to calculate the distribution factor only in the joints because in the ends we can easily say the distribution factor. In the fixed end, the distribution factor will be 0. In the roller or hinged supported ends, the distribution factor will be 1. In this beam, we are having the ends A and C. In the point A, we are having fixed support. So the distribution factor for AB will be 0. In the point C, we are having hinged support. So the distribution factor for CB will be 1. In this case, we have to calculate the distribution factor only in the joint B. For calculating the distribution factor, we have to find the stiffness. Let's see the formulas to calculate the stiffness at the joints. If the ferrand is fixed, the formula is 4EI upon L. If the ferrand is hinged or with roller support, the formula is 3EI upon L. If the ferrand is continuous, the formula is 4EI upon L. Let's apply these formulas and find out the stiffness. From the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the point B, we have to look at the point A. In the point A, we are having a fixed support. If the ferrand is fixed, the formula is 4EI upon L. Here, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I and length is 6. Finally, we are getting EI. Now let's calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. In the point C, we are having a hinged support. If the ferrand is hinged, the formula is 3EI upon L. Here, the moment of inertia is 2I. So instead of I, we have to apply 2I and length is 4 meter. Finally, we are getting 1.5 EI. We have calculated the stiffness K. Now let's calculate the summation of the stiffness. For that, we have to add these two values. After adding these two values, we are getting 2.5 EI. Now let us calculate the distribution factor. The formula is K upon summation of K. For BA, K is EI, summation of K is 2.5 EI. When we apply in the formula, we are getting 0.4. For BC, K is 1.5 EI, summation of K is 2.5 EI. When we apply in the formula, we are getting 0.6. Now let us start making the moment distribution table. In the table, first let us enter the members. Then let us enter the distribution factor values. For AB, the distribution factor is 0 because in the point A we are having fixed support. For CB, the distribution factor is 1 because in the point C we are having hinged support. In the joint B, we have calculated the distribution factors for BA and BC. Let us enter them. Then let us enter the fixed end moments. In the point C, there will be no movement because it is a simply supported end. So MCB is equal to 0. In this case, we have to make CB 0. For CB, the fixed end moment is 20. When we add minus 20 with this 20, we will get 0. We have released CB and we have to give carryover from CB to BC. So half of minus 20 will go to BC. Minus 20 upon 2, we will get minus 10. Let us apply that. Now let us make the adjusted fixed end moments. For AB and BA, there are no changes. For BC, we have to add these two values. After adding, we are getting minus 30. Now let's make the first distribution. The distribution can be done only in the joint. Here there is only one joint, that is joint B. In the joint B, we are having BA and BC. For BA and BC, we are having the fixed end moments. For making the distribution, we have to add these two fixed end moments. Then we have to multiply with the distribution factors. Now let us do the distribution for BA. For that, we have to add these two values and then multiply with the distribution factor at BA. When we do that, we are getting minus 4. Since we got a negative value, we have to enter inside the table as positive. Now let us do the distribution for BC. For that we have to add these two values and then multiply with the distribution factor at BC. When we do that, we are getting a negative value. So we are entering inside the table as positive. Now we have to make the carryover. We cannot make the carryover between BC and CB because we have already released CB and made it as 0. So we can make the carryover only between AB and BA. From BA, half of 4 will go to AB. 4 upon 2, we will get 2. Let us enter that. For AB, there is no distribution, so we cannot make the carryover to BA. In this analysis, we cannot continue further. For BA and BC, there are no carryover values, so we cannot make the second distribution. For AB, there is carryover, but the distribution factor is 0. In this case, we can't continue. Let us add the values and find the final moments. We have to add the values from the adjusted fixed end moments. That is why I have made the color line. We have to add below the color line. When we add minus 40 and 2, we will get minus 38. When we add these two values, we will get 24. When we add these two values, we will get minus 24. So in this analysis, we have calculated all of the moments. In this beam, we have calculated all of the moments. For MAB, we have got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we have got a positive value. That means it is acting in the clockwise direction. For MBC, we have got a negative value. That means it is acting in the anti-clockwise direction. Now let us calculate the vertical reactions. First, I am going to take the span AB and find out the vertical reactions. In the span AB, we are having two moments, MAB, which is acting in the anti-clockwise direction, and MBA, which is acting in the clockwise direction. So when we calculate the reactions, we have to consider these two moments. In this span, first I am going to calculate the reaction RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive, and the distance is 6, so 6 RA. The point load 45 kN is acting towards the point B in the anti-clockwise direction, so it will be negative, and the distance is 4 meter, so minus 45 into 4. This movement is acting in the anti-clockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 32.33 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, we are having three vertical forces, RA, RB1 and 45. RA and RB1 are acting upwards, so both are positive. 45 is acting downwards, so it is negative. We have already calculated RA, which is 32.33. We can apply that. Finally, we are getting RB1 12.67 kN. Now, let us take the span BC and find out the reactions. In the span BC, we are having only one moment, MBC, which is acting in the anti-clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. In this case, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RB2 is acting towards the point C in the clockwise direction. So it is positive and the distance is 4 meter. So 4 RB2. The UDL is acting towards the point C in the anticlockwise direction. So it will be negative. When the UDL comes, we have to multiply with the distance and the distance by 2. So 4 into 4 upon 2. The moment 24 is acting in the anticlockwise direction. So it will be negative. Finally, we are getting RB2 is equal to 36 kN. Now let's apply this rule and find out RC. RB2 and RC are acting upwards, so they will be positive. 15 kN per meter is acting downwards, so it will be negative. When the UDL comes, we have to multiply with the distance to get the total load. When we do that, we are getting 60. RB2 we have already calculated. We can apply that. Finally, we are getting RC, which is equal to 24 kN. In the point B, we have calculated the reaction 2 times. Let us add both of them. After adding, we are getting RB is equal to 48.67 kN. Now let us make the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A towards the point C. In this case, I am moving towards right hand side. Upward forces will be positive and downward forces will be negative. You can see the calculations here. Now let us make the shear force diagram. For the positive values, we have to draw the diagram above this line, and for the negative values, we have to draw below the line, and we have to mark as positive and negative. Now we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram, then we have to combine both of them to make bending moment diagram. For making the free moment diagram, we have to consider every span as a separate simply supported beam. In the simply supported beam, if the point load is not acting on the center, we have to split the beam into two parts, A and B. The formula for the maximum bending moment under the load is WAB upon L. Here W is 45, A is 2, B is 4, L is 6. When we apply in the formula, we are getting 60 kN meter. If in the simply supported beam, UDL is acting for the full span, the formula for the maximum bending moment is WL square upon 8. Here W is 15, L is 4. When we apply in the formula, we are getting 30 kN meter. In the simply supported beam, we know that if the point load is acting, the bending moment diagram will be in the shape of a triangle. If UDL is acting, the bending moment diagram will be in the shape of a parabola. Now let's see how to make the end moment diagram. Using the end moments, we have to make this diagram. First, we have to draw these curves. MAB is acting in the anticlockwise direction, MBA is acting in the clockwise direction, and MBC is acting in the anticlockwise direction. Now we have to see the direction of the curve. All the three curves are indicating upwards, so the points will come above this line. Let us mark them, here 38 and here 24. In the point C, there is no movement, so here it is 0. Then we can connect. Even though we are having two movements in the point B, we have to make only one point because both of the arrows are indicating upwards. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the values are coming above the line. That is why it is negative. Now we can combine the free moment diagram and end moment diagram. Wherever they are acting alone, we have to mark the sign with the values. If they are acting together, we are not marking anything. We just keep the space empty. If you are very experienced, no need to make the free movement diagram and end movement diagram. You can make the bending moment diagram directly. Now we are going to end this session. Thank you for watching this video.